Welcome everyone. Today marks one of the most exciting milestones in your journey as a BSIT student. We are diving into data structures and algorithms, often called DSA. If programming were like building a house, data structures would be the materials, the bricks, wood, and glass, while algorithms would be the blueprint and the step-by-step instructions for the workers. Without these two, your software might work, but it would be slow, disorganized, and prone to breaking. Have you ever wondered how Google finds your search results in milliseconds, or how Facebook suggests friends among billions of people? It's not magic, it's efficient DSA today. I'm going to show you how to think like a professional engineer, organizing your data logically and solving problems with mathematical precision. By the end of this session, you'll see that code is more than just syntax. It's about structure and logic. Let's start by looking at what we aim to achieve today. Before we set sail, we need a map. Our goal today is twofold. First, we will demystify these big words. We'll define what they are without the heavy academic jargon. We'll then learn how to categorize different data structures. Basically, how we store information in the computer's memory. We'll also look at how algorithms serve as the recipe for problem solving. We're going to look at specific examples of searching for information and sorting it, much like you would sort files in a folder. Finally, we'll discuss why efficiency is the holy grail of information technology. Why does it matter if a program takes 1 second or 10 seconds? In the world of banking or hospital systems, those seconds are everything. We've got a lot to cover. So let's get our foundation solid by asking the big question: what exactly are these two concepts? Let's break it down. Imagine a library. If all the books were just thrown in a pile in the middle of the room, that would be a terrible data structure. You'd never find anything. A library uses bookshelves, categories, and labels. That is its data structure. Now, if you wanted to find a specific book, say a biography of Steve Jobs, the path you take from the entrance to the shelf is the algorithm in your computer. A data structure is how we hold information like your Spotify playlist or your bank balance. The algorithm is the code that plays the song or deducts the money when you buy something. Think of it this way: data structures are the nouns and algorithms are the verbs. You need the right noun for the right verb to make a sensible sentence. Now that we understand the definitions, let's see the different ways we can organize these nouns. In information technology, we don't just use one type of container for everything. We categorize them based on how they connect. Linear structures are like people standing in a line at a cinema. One person is always behind another. It's a simple, predictable sequence. Common examples you'll use in your first coding projects are arrays and lists. On the other hand, non-linear structures are more complex. Think of your family tree or a map of subway stations. These don't follow a straight line. They branch out or loop back. Why do we have both? Because some problems are linear, like a list of your recent transactions, while others are non-linear, like the suggested friends algorithm on social media, which looks at a web of connections. Choosing the wrong one can make your program incredibly slow, almost like trying to find a specific person in a crowd by making everyone stand in a single file line first. Let's look at the most basic linear structure first, the array. Let's talk about the two most common ways to store a list. The array is your best friend. Imagine a row of school lockers. They are all right next to each other, and you can jump straight to locker number 10 because you know exactly where it is. It's fast, but it's hard to add a 21st locker if you only build 20. Now consider a linked list. This is like a scavenger hunt. You find the first clue, and it tells you to go to the park. At the park, the next clue tells you to go to the library. The items aren't next to each other in the computer's memory, but they know who is next in line. Linked lists are great because you can easily add new clues or items anywhere without moving everyone else. However, searching for the 10th clue takes time because you have to read clues 1 through 9 first. Can you see the trade-off? Speed versus flexibility. This is a common theme in it. Next, let's look at two more linear structures that follow strict rules: stacks and queues. Sometimes we need to enforce rules on how data enters and leaves. The stack follows the LIFO rule: last in, first out. Think of a stack of plates in a cafeteria. You always take the one from the very top, the one that was put there last. Your undo button on your computer works exactly like this. The very last action you took is the first one that gets reversed. Then we have the queue, which follows the FIFO rule: first in, first out. This is exactly like waiting in line at Jollibee or Starbucks. The person who got there first gets served first. Computers use this for printing. If you send 5 documents to the printer, it prints the first one you sent, not the last. These structures are vital for ensuring that data is processed in a fair or logical order. Now, let's move away from these straight lines and look at the branching world of nonlinear data. Now we enter the world of complex relationships. Trees are everywhere in it. Look at your computer's C drive. You have a folder which has subfolders, which have files. This is a hierarchy. The root is at the top and it branches out. Trees allow us to search through millions of items very quickly, because we can ignore entire branches that we don't need. Finally, we have graphs. Graphs are the chaos of the data world. There is no top or bottom. Everything can connect to everything else. Think of a GPS. Every city is a node, and every road is an edge. To find the shortest path from Maramag to Davao, the computer uses a graph algorithm. Or think of Facebook. You are a node, and your friends are connected to you. Graphs are powerful because they model the messy, interconnected reality of our world. But having data is only half the battle. How do we process it? That's where algorithms come in. We've organized our data. Now let's give it some verbs. An algorithm is simply a step-by-step procedure. If you've ever followed an IKEA manual to build a desk, you've executed an algorithm. But in it, a good algorithm has specific traits. It must be finite. It can't run forever, or your computer will freeze. It must be definite. The computer doesn't understand maybe. So every instruction must be perfectly clear. And most importantly, it must be efficient. Imagine if you asked Google Maps for a road to the mall, and it took 3 hours to calculate it. The mall might be closed by then. We measure algorithms by how fast they work and how much memory they take up. As a BSIT student, your goal isn't just to make the code work. It's to make it work well. Let's look at one of the most common tasks an algorithm performs. Searching. Suppose I ask you to find a specific name in a pile of 1,000 unorganized papers. You have to look at the first, then the second, then the third. That is linear search. It's slow, but it works when there's no order. Now, imagine I ask you to find a word in a physical dictionary. Do you start at page 1? No, you open it to the middle. If the word starts with S and you are at M, you know for a fact the word isn't in the first half. You throw that half away and repeat. This is binary search. In just 20 cuts, you can find one specific item out of a million. But there's a catch. The data must be sorted first. This is why we spend so much time talking about sorting. If our data is a mess, we are stuck with the slow linear search. So how do we get that data into a neat order? Sorting is one of the most studied areas in computer science. Bubble sort is the one most students learn first. It's like a line of students where you compare the first two. If the taller one is in front, they swap. Then you compare the next two. The big values bubble up to the top. It's easy to code. But if you have a million items, it's painfully slow. Professional systems use things like quicksort. Quicksort picks a pivot point and says, everyone smaller than this go left, everyone bigger go right. Then it repeats. It's like a professional dealer at a casino sorting cards with lightning speed. Whether you are sorting your emails by date or your Shopee search results by lowest price, a sorting algorithm is working hard in the background. But how do we prove one algorithm is better than another? This is the advanced part of today's lesson, but don't let the math scare you. Big O notation is just a way to describe how much a program slows down when you give it more work. Imagine you have a robot that cleans a room. If adding one more piece of trash adds 1 minute of work, that's on linear. It's predictable. But what if, for every new piece of trash, the robot has to clean the whole room? That's on. And very quickly, the robot will never finish. In the BSIT world, we always want our code to be efficient. We use big O to say, hey, this algorithm is great for 10 items, but it will crash the server if we have 10 million. Understanding this helps you write code that doesn't just work on your laptop, but works for the entire world. Let's bring everything we've learned together. We've traveled from the very basics of lockers and scavenger hunts to the complex world of algorithmic complexity. The big takeaway is this: data structures and algorithms are inseparable. You can't have an efficient search if your data is a mess, and you can't build a massive social network without understanding graphs and trees. As professionals, your job is to be an architect of information. Every time you use an app that feels smooth and fast, it's because an engineer chose the right data structure and a clever algorithm. This is the difference between a beginner who just scripts and a professional who engineers. Before we wrap up, I want you to think about how this applies to your life outside of this classroom. I'll see you next time when we start writing the actual code for arrays. Class dismissed.